So what I'm going to be talking about is quantum registers, and more generally registers, and I will show you what that is. But so the very rough overview of this talk is, why do quantum registers, what made me sad about how quantum registers are used? And then the second part is how I got happy again. Probably.
Maybe the story of the pen will be the same.
Yeah. Okay, so to illustrate the problem I have, let me give you show you a very small quantum problem. And but first, who knows something about quantum? Yeah, so a lot of people know a little bit, but no one is saying, yeah, me. So we will not need to go into very deep quantum mechanical things. And if you see something like this, you can also imagine everything to be actually classically. So you can imagine that here we have these 3 wires here, 4 wires, which could just be carrying classical data, and then H is some operation on this classical data. I mean, there are not many operations on a single bit classically that you can do. Quantumly, there's more. And then here we have an operation that is on 2 wires. And if you know quantum, then on the Y wire, this happens to be the so-called Hadamard operations, and on the XZ, it is a so-called C0, only the other way around, as it's then its canonical form, because the control is the lower thing. But basically, this is a very simple quantum circuit. I've also written it here on the side programmatically. And so we are applying H on the Y wire, and then we are applying C0 on ZX, not on XZ, because C0 is not something symmetric. So think of it as just mutable variables if you don't know quantum. Now, the problem is that if I want to actually write down formally what this is, what I have to do is to formula, I mean, the H is just a unitary transformation on a 1-qubit system, 1 quantum bit. But if I want to write down the semantics of this whole program, I need to say, what is H seen as an operation on the whole system? Well, this is pretty easy, one would say, because we have tensor product. Tensor products is basically, in quantum mechanics, has the effect as just doing 2 things in parallel. In the classical setting, the analog would be just the product of 2 functions, so 2 inputs in parallel to 2 outputs. So I can just write this. This is the identity on 1 qubit, tensor, the Hadamard tensor identity on 2 qubits. Very easy. Now I need to do the same with the C0. Unfortunately, the C0 matrix is basically a matrix that works on 2 consecutive bits. So what I need to do is actually first I would need a swap operation, because I cannot, there is nothing in the system where I actually apply C0, because C0 would be something that I can apply to 2 wires next to each other. So I would need to actually first swap wires around, then do the C0, then swap it back. So I can define this operation swap that swaps 2 wires, and then I can actually build up the C0. And this is this expression. So this is already rather unreadable. Yeah, but it's kind of natural what is done. And if you are tasked with writing down the formula for the C0, you will probably come up with this or with something equivalent. But actually doing this from hand is already quite annoying. And now the thing is, we are not really done yet, because if we are really formal and we can't just say, oh, without loss of generality, the tensor product is associative, then we have that there in the corner, or there in the corner. So H tensor K tensor L is not the same as H tensor K tensor L. They're just isomorphic. So I actually would need to plug in the isomorphisms for that too. So let's define an isomorphism U alpha that is just the recurrence in it, and then we write down this little thing here very easily as this sequence of operations. And you see, this is really horrible to work with. So the question is, can we somehow, so we have these X, Y, Z, they are, at least in intuitive sense, just some parts of a quantum memory, and then we have operations on them. Can we anyway kind of nicely say what it means to have an elementary operation applied to some of the registers in the system? Yeah, this is a solution to this problem, but it's definitely not a nice solution. Yeah. So this is what the starting point why I started being annoyed with registers.
What is a register then?
I mean, I don't have a formal definition of what a register is. I mean, I will have one, but I don't have one. But in the intuitive literature, a register is just a part of a quantum system. So in this case, X, Y, Z, and W are 4 registers, quantum registers within a quantum system. So it's
the wires.
It's wire. In the picture, it would be wires. Although you could ask the question, if I have 2 wires and I put them like close to each other, is that 1 register or 2 registers? These are also subtleties which are usually not resolved because it's kind of obvious that we can see them as one when we need. But it's something that is formally not really obvious. One way to say what a register is to say, well, our whole system is just written as a tensor product of subsystems, and the register is basically like one of the arguments to the tensor product. And then there are definitely 4 registers here, but then definitely X, Y together is not a register and so on. So this would be one possibility to say what a register is, but one that is very rigid because it depends very much on how I've written my state in the first place. And if I would write the state in a different form, for example, X tensor 1 in Y in parentheses, tensor Z, tensor W, then strictly speaking, X and Y are not registers, but X tensor Y. So it's kind of messy, and it's all non-messy when you kind of drop all isomorphisms, and it's in the like not fully formal literature, like in cryptography, for example, there's never any trouble with that. But if you want to formalize it, you get into all kinds of annoying encoding issues. Yeah, so to summarize what the problem I've noted here is like addressing registers, meaning I want to, for example, say I have an operation on this register, is something that can be really complex, even in very tiny programs, because often we need operations that work on 2 registers simultaneously. And in that respect, it's a bit different from the classical situation. In the classical situation, it's easier because if I say, for example, I want to have a swap of X and Y, I could break it down into one operation where I say read X, then read Y, then swap, and then write Y to the first register and X to the second. So it's each operation is on one separately. But quantumly, I cannot actually break things apart. So I will need to apply some operations to a bunch of registers jointly. And that, as you've seen, can be very complicated to write down explicitly, especially if you want to make it in a theorem proof or something. What we write down is actually looks more to me like some compiler output than something that we would want to have as part of our semantic definition. Yeah, so basically, the equation that was written here, this long thing, I'm fine if this appears somewhere in a proof or in a calculation, if it has to, but I don't want this as part of the specification what the C0 gate is doing, because then I really have no clue what it's doing. So I could generate these formulas, but then I would have to say actually what does the thing I want actually mean in the first place before I can actually make a compiler into that thing. So that's kind of the unfortunate situation. Then there are other easy things that people usually do with quantum registers. So for example, they might say, we apply U to the register X in the diagonal basis. What does that mean? Well, the register is basically the content of a register is a vector space, and you could see kind of the same register, but the vector space up to an isomorphism represented with respect to a different basis. And something like this, you would intuitively say, well, this is also kind of a register. Because there's no like physical reason why one of them is more natural than the other, except maybe we started out defining the system as one, and then suddenly the transformed one is not a register, but informally you can treat it as one. An example from physics is also, maybe you know about the position momentum duality. So the position of a particle can be described as a quantum state, and the momentum also as a quantum state, but actually the position they are you can actually give only one, so it's just two different representations, and if you know the quantum state position and you do the Fourier transform, you get the momentum and vice versa. So it's actually two ways of looking at the same thing. So if I would say this part of the big system is the momentum, is the position, I would be equally justified in saying no. The elementary thing is the momentum. So they're both kind of subsystems, and we don't usually call them registers in that setting because this registers is a word we use more in quantum computing. But actually, like if we step back from small details like in which community we are, it's also the same thing. So would be nice if we formally could treat like different views on the same variables both as the same kind of the same formal quantum concept. Or something else that we happily do is like, let's say if X is, I don't know, a 5-qubit register, then X5 would be a register referring to the 5th qubit. Yeah, intuitively, yeah, because a part of the system is a part of the system. Again, it gets very difficult to like write down what this actually means formally. Is it a different concept? Do I have to actually always write down the chain, or can I give a definition what a register is that would encompass that? Or then pairs of registers. I might say I have X and Y, and I do some operation on it, on them together. Now, I might write my program language and have some explicitly in the semantics or in the syntax of the language. I can say there are registers, and then there are lists of registers, and I can apply operations to list of registers. But intuitively, X and Y together are also just a subsystem. So if I could just treat those two together as a register in its own right, that would make things much more uniform and simple. And the position momentum example I already mentioned, turns out I have it on the slide. Should read my own slides first. Okay, so this is kind of this gap between what we informally do very happily when we are talking about quantum circuits and the mess we are in when we are trying to do it formally. So there are approaches, like I already mentioned the swap associators thing. You could also say, well, my quantum memory just consists of qubits, and any register is just a certain, like a list of indices of qubits. But as soon as you want to go beyond some like very low level programming language kind of thing, I mean, this is like when you were in some classical language, and any data type has to be a collection of bits. This would include even an option type or something which doesn't have a power of 2 as its cardinality, and it definitely doesn't work with infinite data types and so on. What did I mean by tensor group? A family of spaces? Yeah, this is basically the thing that I just, every register is a space. I tensor them together, and it's just completely rigid. And all these approaches, for the reasons I already told you, I don't like. So my question was, can we do better? So what we want is, we want to answer the question in an abstract way, what is a register or a quantum register? I mean, I will later show you that actually the solution is not limited to the quantum case, can be useful also for the classical case or maybe other cases that I haven't thought of. I wanted to capture all these informal examples that I have shown you. I want a clean abstract definition, not something like a register is internally of tree of projectors or whatever, of unitaries and whatever. I would like it to be independent of the memory model that I start with. So it shouldn't matter whether I have defined things as a tensor product of several things, and the registers are like these tensors. If I have written it in an isomorphic way, I should still be able to refer to the parts of the memory and not be stuck with that thing. And I want it to be easy to formalize. So, for example, in a theorem prover like Isabel Horn, which I like to use, but I mean, basically, Isabel Horn is kind of the gold standard in that way because it doesn't have dependent type. So if you can do it there, you can do it everywhere. Yeah. And actually, this is not just what we want. These are the results. This is all of this can be achieved, and I will show you how. And actually, the same definition works for classical. I mean, not the same definition, but the same generic theory. And in order to understand how registers work, let me first look at the classical registers. So how can I define a classical register in some more generic way? So, I mean, generally, in terms of the types, a register is like the type of registers would be parametric in two types, namely, what is the type of the memory in which it lives, and what is the type of the content of the register. So we may have, for example, memory that is maybe 1000 bits, and my register is 5 bits. So even if I'm not asking like which 5 bits, I mean, the first thing I say, it's like 5 bits within 1000 bits. So A here is the content, and M is the memory into which it points. And I can define a register classically, or a variable, or a record entry or something, with a getter and a setter. So this is not something, some very new insight. And the getter would just be a function from memory, from M to A, from memory to content, and the setter would take a memory, a new content, and give me the new memory. So this actually fits into our general framework. However, it is not the representation in which this is most obvious. There's a different way that is equivalent to specifying a getter and setter, namely by giving an updater. I'm not sure I mean, this doesn't sound very good. I don't know, maybe there's a better word. So basically, if I give you a function, how I operate on A, it gives me what this does to the whole memory. And I can, well, obviously reconstruct the setter from that by just putting in a function, a constant function. Can I get the getter back? In general, not. But if I slightly tweak this and say my updater can take a partial function, and then it outputs a partial function, then I can kind of reconstruct the getter because I just put a function that says, well, I'm only defined at the value 5, and then I can use this to find out whether my variable has value 5, and then I can reconstruct the getter from this. I mean, I'm not sure whether I can do it in a constructive logic, but in a with classical logic, I can definitely just reconstruct the getter from this as well. So I can therefore define a classical register as a function that takes a partial function of A to a partial function of M with some natural properties. For example, if I apply G and F, first G to the register and then F to the register, it's the same as applying F after G to the register. And there are a few more. I mean, you can write them explicitly down. They're all natural. Takes a bit of thinking to see that they are actually all that you need, but there's no really surprising property. And I don't want to go into these because there's nothing exciting, but it's important to kind of get this idea because then in the quantum setting, we have a very similar idea as to this update. So maybe there are any questions here.
So, how do we reconstruct the getter? Like we just put a function that is facing every input, but the one.
Yeah, I mean, the first thing I can do is basically a tester. I can define a function that, given a memory, tells me whether the register contains a specific value. And such a test I can make by putting in the argument for the updater is just something that is defined only at the value, at that specific value that I want to test against. Then the returning function will also be defined only at memories that have that specific value in the register.
Because of some property we're asking of the updater, or
yeah, because it behaves nicely. I mean, the intuition is if I evaluate the updater and it fails to work on that, then it will fail. And then I can define the getter as just the value for which the updater, the tester will be satisfied. Yeah. Okay. So now I want to do a similar thing in the quantum case. So I want to construct a quantum register. So first, in terms of just the types, now the memory and the register content, classically they were described by sets. Like we have the set of possible values in the memory, we have the set of possible values inside the register. In the quantum setting, we have the space, the space of states of the whole memory, and we have the space of states of the register content. At least that's kind of the things that we want to relate. And one of the what we actually wanted to achieve, or one of the aspects we wanted to achieve, is that if we are given some operations that we apply to a register, let's say, for example, we had this example, Hadamard on register Y. So what the register formalism at least needs to tell us is, given U applied on register X, what is the operation of the whole system? So it should map a unitary to the whole system. Yes?
By space, you mean the Hilbert space? Or...
Yes, it's a Hilbert space.
Okay.
And so this is something we should, the registers have to at least do. But now remember from the slide before, we had that this is very similar to actually the updater. Yeah? We are given an operation on the contents of the register, and we need to translate it into an operation on the memory. This is exactly what we did with the updater. So let's try to just say, this is how we define a register. Yeah. So we could say, a register is a function that takes a linear operator on the space of the register content to a linear operator or linear function to the space of everything. And then we ask, why linear? Why not unitary to unitary? Because we want to map unitaries. Well, it turns out that we might want to map other things, and our definitions will satisfy by the properties later that a unitary will indeed be mapped to a unitary, a projector to a projector, and so on. But in terms of the type, it just maps any operator to an operator. Or, I mean, I'm explaining everything in the finite dimensional case because the infinite dimensional case is more complicated. In the infinite dimensional case, it would be bounded operators to bounded operators. But yeah, it's a bit distracting from the actual ideas to look at the infinite dimensional case. I will, from now on, never mention it unless I'm explicitly asked. Okay, so does that work out? Well, we need to add some properties, and it turns out there are just 3 properties that we need for a register in the finite dimensional case to be meaningful. Is that it's linear, so it linearly maps operators to operators. It's multiplicative. Multiplicative is definitely something that follows from the intuition, because it means if I apply 2 operations in a row on the register, it's the same as applying the composition of them to the register. So this was also what I had written in the classical case. And it should be compatible with the adjoint operation. So I don't have any strong intuition why these 3 properties. They're just the properties that you need to use so to instantiate the general framework that I will mention.
This is identity, master identity.
Yes. How does it? Wait, does it? Oh, have I forgotten to write this? I mean, this is a requirement for the registers. The identity has to map to the identity. Now I don't remember off the top of my head whether I should have written this, whether I dropped it from the list or whether it was included. I can find that out rather easily by actually looking at paper.
Inverse operations, is that if you compose something that's inverse?
There's only there's the diagram.
That's the wrong section. Quantum registers, page 9. Yeah, I have it explicitly here. F of 1 is 1, so I just forgot to put it there. Yeah, I have a simple example of something that satisfies the properties that I have on the slide, and that is not unital, namely the zero function. It's linear, it's multiplicative, it's data preserving, so it's obviously not okay. So yeah, I forgot one of the function of the things, but okay, thanks for that question, because I actually overlooked something in the slide. So that would be the definition, and now let me try to explain why this is nice. I mean, at first, okay, one thing that don't have on this slide, but the first question you have to can ask yourself are like the most elementary constructions of registers actually registers. So, for example, when you have like 4 wires, is the second wire a register? Well, the interpretation of a register for these very concrete cases is obvious. I already had it. It's like identity tensor, like X is mapped to identity tensor X tensor identity. So I just need to check that this function satisfies the axioms, and then I see yes. So some basic constructions of registers satisfy it. So that is good because it shows that quantum registers actually exist. I didn't define something vacuous. But additionally, I want that I can make that they behave nicely. Like I want to, because I said I want to do all kinds of operations with them. Well, the first thing is they behave nicely in the sense that they make it very easy to define semantics, for example, of languages. For example, if I give the semantics of apply U on a register X, the semantics is just X applied to U. So that's one very useful thing. This also works with other things like measurements. It's just by applying X to each of the projectors and so on. But the thing that is more interesting is the pairing and the chaining, as I call it. So pairing is actually something that I found like actually quite hard to get going in a general way, and which is kind of was one of the big motivations. It's when X and Y are registers and they're compatible in some way, and I will come to details of that on the next slide, then X and Y together is well defined and does in some way represent the registers X and Y together as a single register. And if I have that, I can just take, for example, in our initial circuit, X and Z, the registers, and make them together and say, okay, that's now a 2-qubit register, and on this will apply C0 without any operators going on.
You should read this semicolon as a sequence, so it's more like a parallel composition.
Yeah, it's kind of it's like a pair, but not like it's not a pair of registers. It's a parallel composition is maybe the right thing, or you could think of it as a concatenation or something. In the classical setting, it would be very much like actual pairs of values, like in the getter would, for example, be just get this, get that, give it as a pair. We cannot write it in that form, decompose it in that form in the quantum setting. We can only show that it exists and it is nice and so on. Yeah, I mean, actually, specifically when you talk about quantum registers, again in the informal literature, I think people would just write X, Y, just write them next to each other. And then we have another operation is also very useful for chaining. So because the register is with respect to some memory space. So if you have a register, like let's say you have a big memory, then you have a 5-bit register, then you can also define a register like the 5th bit of a 5, which is a 1-bit register in a 5-bit memory. And now you can put them together. I can say 5th bit of 5 within 5-bit register X. And these together, this is a 1-bit register in the whole memory. Yeah, and then we can also do these things like if something is a register, it's also a register when I basis transform it. Technically, this is because the basis transformation itself is a register, and then I can chain it with the register I want to transform. Yeah, and I can combine these things widely together, which gives me complex things that would be very hard to describe by explicit sequences of all these unitaries for swapping and so on. Okay, let me say a bit more about the pairing. I'm not going to show the existence, but kind of what it does. So the thing is, pairing two registers is not something that is meaningful in general. Even in the classical setting, it's not meaningful to say I have a variable x and let's say I pair x with itself. Because what happens if I assign the pair 1, 2 to xx? What's supposed to happen? Could of course make some conventions like, well, the second value overrides the first and so on. So you could come up with something, but it will be then asymmetric and will not be equivalent to the other way around. And I also am not aware of any quantum way that makes any sense if I would say that I have a variable register x and apply to xx a 2-qubit operation or two, I mean, it doesn't have to be qubit, but for example, 2-qubit operation. There is no, I cannot put the meaning even to the concrete, to that concrete case. So what we need is that the registers, if I want to put them together, they need to refer to distinct memory locations. However, distinctness, since our register does not explicitly kind of list, I don't know, bits in the memory, it's not that easy. In the very simple case where I say, well, my registers are just factors in the tensor product, then they're compatible if they're different factors, and they're not compatible if they're the same factor. So it's easy. But then you also ask, once you pair something with something else, then well, you need to kind of flatten out and see nothing appears twice and so on. And in the general case, not so obvious. I could have, for example, the position, the xy, which is a register, and then have x, which is a register. They're not the same, but they're definitely also not compatible. If I put them together, I have x twice. It turns out there's the definition is actually very simple. All I need is that if I have these two registers and I apply f, I apply B, I do operation B on the content of G, and then the operation A on the content of F. This should be the same as doing it in the opposite order. This should be intuitively something we definitely expect from registers that are on several parts of the memory. So operations on them should commute. And it turns out that this definition of compatibility is actually sufficient for getting the whole theory working. Because then we can show that there exists a unique H, so a unique register H, so that if I apply H to A tensor B, so A is applied to doing these two operations in parallel, is the same as doing, sorry, there's a typo here. Magic pen use, yay. It's the same as doing B on G and then A on F. So the H register allows us to do them two operations together on H is the same as doing them sequentially on F and G. Or the other way around, because compatibility says this order doesn't even matter. And this is what we call the pair. And it turns out it works nice, so it has all kinds of pleasant algebraic properties, because you don't want to check this compatibility from scratch. Because this is easy to write but hard to check. But it turns out if you have a bunch of compatible registers, if you take a pair of compatible ones and then this will be compatible to any that is compatible to all the components in the pair. So you actually never need to use this except when you define registers directly from scratch or you are proving general theorems. Okay, so let's use this formalism to revisit the example from before. Is it now easier to write it? Well, one advantage we already have is that we can formulate this more generically. Because before we had to say, let our memory be x tensor y tensor z tensor w. Now I'm just saying, let x, y, z, and w be arbitrary compatible registers in the memory. And I don't even have to say how they're located them, because the whole reasoning, any reasoning I want to do works even if the memory is structured different. But if you want to be concrete, you can just say, for example, x is maps A to A, tensor identity, tensor identity, tensor identity, and so on. But I can derive all my results also generically at no extra effort. And then this is just x of h. And this is zx, my pair of zx of c naught.
Surely it's y of h.
Definitely it's y of h, yes. Otherwise, I would say my formula is a bit unintuitive. Yes, it's y of h. So you can do this. And then you can also derive things kind of already generically on that. So for example, from the compatibility of those registers, we also get that y and zx are compatible. And that means, by definition of compatible, that this C0 and this Hadamard commute. I mean, it's not very surprising. But if you prove that on this long sequence of swaps and so on, it's a tedious calculation to see that they all cancel out in the right way and so on. I mean, they will, it's elementary, but it's tedious calculation kind of elementary. So you get that for free. And you could, another advantage that doesn't really come out in this tiny program yet, but you can do something kind of like focusing on subprograms. So let's say there's a lot more going on here around. And now you want to show that maybe this thing equals something else. So the problem is that if you compute like the whole semantics of this thing, you live in a very big space, maybe an infinite dimensional one where you need to reason about infinite operators as opposed to just a few qubits. However, what I can do, again, just by using the laws of registers, I can just rewrite those two operations. I mean, now imagine they are not commuting because this is a trivial case of borrowing. But let's say this composition does something else interesting. So I can rewrite this, for example, as x, y, z of identity tensor h tensor identity, for example. I mean, the multiple pairs just nested pairs. This follows generically from the properties of registers, even in the non-quantum specific case. So if you write this, I can write it in this form, and then I can write the C0 as, I could also write it as x, y, z of, well, in this case, it's something huge, because it turned out that it's, oh, I could actually be cleverer. Let's say I start with this one and I want to do it nicely. So I could say, I could also represent this as zx, y, because the order is completely arbitrary. And then this becomes C0 tensor identity. And then this one, I could write in the same space. And this one becomes identity tensor Hadamard. And now it's the same register. And now I can multiply them together and I get zxy applied to the product. And maybe then I work explicitly with matrices to find out what it does. But I managed to project onto some subpart of the system, which is especially important if I want to maybe automatically compute something just by computing the matrices. There you want to have small matrices and just having the fact that there is some tensor product, it's just distracting.
So just to check if I understand the notion of compatibility correctly, those expanded versions, will they still be compatible?
With each other, you mean?
Yes, so
I mean,
the expanded H and the expanded C0, will they still be compatible?
No, they wouldn't. I mean, the ZXY, I mean, here we have now the same register. We have ZXY and ZXY. This is representing ZXY with H. And that's the same register, so it cannot be compatible, except in the degenerative case of a zero-dimensional register, one-dimensional register. So we don't get, in this representation, we don't immediately see that they commute. we can still see that they commute because we can now use the multiplicativity. So we have that this is the product of this is zxy applied to c naught tensor I times I tensor h. And now you have but this uses the fact that here we have some commuting things. And in the general example, we don't want everything to compute. So you can wrap and unwrap, and maybe sometimes you will also not like to have these long tensor products, because maybe now you have done this focusing on 3 registers, and you don't want, and writing it as a tensor product is again unreadable. You could then also rewrite, for example, a different way how it could rewrite this y of h could be, for example, the xyz term applied to, and now I can define the register like a second component from out of 3. That's a well-defined register. So it's like if I have a 3-byte state, second one, so I can actually write that this is the same as second out of 3 applied to Hadamard. So I can also switch seamlessly between explicit tensor products and tensor products where I'm kind of just pointing at an index. That can also be very useful if you have tensor products where there's just one component, but you need to be concrete for some algorithm because the x, y, z, and w maybe they're completely abstract. So they're completely abstract registers. I can still represent things as with concrete registers. And all the things that I'm saying here, they hold very generally. So there's just a bunch of laws about register categories that allow me to do all these rewritings. Yes.
Can you go back to what you just said?
I'm trying. I'm working hard on it. Yeah.
So at the beginning, when you were explaining the infelicities of the notation that you started with, you made the point about the problem of associativity of the tensor product. And then here you wrote this non-associated tensor.
Yeah.
I didn't see how we were able to get this.
I did. Actually, this is, if I'm saying that these pairs here are just nested pair, and I'm saying they're left associative, then these examples are actually completely correct with the associative with the non-associative tensor product. Okay. Because this is just a so if you look here, so it would be zx paired with y, and then c naught is on the zx type paired with a one-dimensional identity. Or here we have zx, the corresponding identity is the 2-qubit identity, which is which fits that type, and h fits that one. So if but this assumed then, so I was in my head putting parentheses there. So in order to be able to write this, I will have to fix an order of parenthesizing, and then it will be formal. And there may be situations where then, if you want to relate things that are parenthesized differently, those will be different registers. And if you want to relate them, indeed, you will have, for example, that zx y of a is actually not the same as z.
So can I just ask a quick, I mean, it seems to me that this associativity is like just bureaucracy, no? Because I mean, the qubits care which way you put the parentheses, I guess they don't.
No, the mathematics cares. I mean, you just can't even type it easily if you want to really formalize it.
Right.
It's different spaces, and it is common in informal mathematics. It's common to just say we don't care about isomorphisms, but there are 2 interpretations of what this means. One is it is left to the reader to insert them, and the reader leaves it to the author to make sure that the reader could have inserted them. So
there is only one way to insert.
Yeah, hopefully, yeah, or maybe only one with which the proof actually doesn't fail or whatever. And then there's the second view where you say, okay, we have actually a very powerful logical system in which we actually can treat things as the same. I mean, I'm not very familiar with it, but homotopy type theory seems to attempt things like that. Not sure would help for this, but in general, but I don't want to rely on things like that, or on the necessary, or on defining. I forget whether strict or non-strict was the one, but categories in which the tensor product is actually associated. I want to avoid all that because this is actually extremely heavy machinery, just to avoid putting the like if you're really formal, this is extremely heavy machinery. Yeah,
Yes, my question was instead of doing type theory or something that complicated, I guess, if one does a type theory for symmetric numerical categories, then one could get some syntactic terms that actually expands what this.
Yeah, I mean, I have never tried to define a symmetric monoidal category with an associative tensor product.
They all, sorry.
Yeah. But I wouldn't even know how to start. Like, I mean, I'm definitely sure that in Isabelle Hall, where I'm most familiar, I just cannot write this. I cannot write down, define a type modulo isomorphism between different types. There's no way I can even write this type.
This is okay. I think I think you'd be able to do a similar thing with the symmetric model categories, but you trade the explicit permutations there for having the list of variables or of registers in front of every operation here. So it's going to
yeah, I mean, you get if you work with symmetric modular economy, you still have the explicit swapping.
Yeah.
If you write the question is, can you get rid of the associativity operations?
Yeah.
And I'm not even, because the thing is, if I have a type, let me switch to this. So let's say I define some tensor product operation, and this will have some type, which will be maybe something like, there's one operation on types, which sends T and U, okay, it sends a type and a type to a type. And then there are other operations. There's the operation on the elements, so it sends A, alpha and beta to an element of alpha tensor beta, for example. And if I write this like this, I mean, I need to construct something that we actually have that T1 tensor T2 tensor T3 is equal to T1 tensor T2 tensor T3. I don't know how you can define such a type so that the type checker will, I mean, it would have to accept them even as definitionally equal, otherwise I cannot use this constant, this operation on the second line in the context where it's the other time. I mean, I'm not an expert on these type theory things, but I
just lists have this property, right? Like the free model works this way.
So it's like one of types, one if you guys have a list of types.
I think it might be okay.
I mean, one has a list of types. I mean,
yeah, but lists have it. I mean, this is then specifically on the.
this is the construction of the free model type.
Yeah, so your collection of types will be the free monoid over your some basic types, right? And then you've got the strictly associated tensor product.
I'm not fully sure which. I mean, would you be able to do this with Hilbert spaces, for example?
Well, the Hilbert spaces are, I don't know, are Hilbert spaces a strict symmetric monoidal category?
Even if
It depends how you construct this category. I mean, you have to construct it first. So, I mean, you can construct. If you can talk about finite dimensional Hilbert spaces and say every Hilbert space in my category is just complex C to the n for natural number n. And in this category, I can define very easily the tensor, the associative tensor product by just saying like C to the n and C to m goes to C to the n times m. The same way I can also take the product easily associated, but I don't know.
You need infinite dimension.
I want infinite dimension, and even in the finite dimensional case, I prefer not to use the C to the something representation because that one is it feels a bit untyped. It's kind of the same as if I would have a language where in my language any two types that have the same cardinality are the same type. This allows me to accidentally write very wrong things because I mean I don't want a RGB like red, green, blue to be the same thing as bool option because I see them as different.
That's not the category of
no, but this would be an example. Similarly, if I wouldn't want the quantum data structure, which is a position of red, green, blue, to be the same type as values that have some true, some false, and none.
This is a different thing, I guess. My complaint is that's not what we were talking about. I don't understand what this is meant to model. Is it a quantum programming language with the semantics in Hilbert spaces, or is
It's
it
more a foundation for that. I mean, I can use this to actually write down a quantum program, an imperative language. I mean, I've done that, but what I've shown you here is basically understanding what it means to be a part of a system. And now the question, the sidetrack that we are on is more the question: can we formalize a strict monoidal category in some picky software, like not convincing mathematicians, but convincing someone like Cox.
Let's have this discussion after.
sure?
Yeah.
Oh, I thought we were done.
Yeah, I mean, I'd be happy if you can show me like a concrete example of doing that.
So basically, I wanted to point out one thing was that instead of going for quantum tech theory, there is work by these type of theories for semantic categories that I think maybe people are the ones who are disobeying.
Yeah,
Maybe those could be used or related to it.
maybe. I mean, one goal that I have here is I want something that does not rely on some very specific theoretical foundations. Because if now you tell me, yeah, but you can, I have a solution how I can say what a register is, but you can only use this solution if you go to that theory approval that has the following like very powerful categorical structures built in and so on. Then I say, well, it's not really satisfying because then I'm stuck with that. It's an approach just for that. While this approach, it works everywhere. It works even in simple type theory. So this is kind of also one of my goals. I'm not saying it's impossible to do elsewhere. I have the feeling it is still simpler than what you could do with these powerful tools, but I'm definitely open to discussions of like concrete examples. I just don't actually know a lot about those things either, about those like category theory and dependent types and whatnot possibilities. So I may be overlooking something, and I'm really happy to talk about this. Yeah, but let me get back maybe to this now. Okay, this slide is too full now, so let's go to the next one. So I mentioned that actually this is more generic. So I have shown to you how I can define quantum registers. I've shown to you how I can define classical registers. It turns out they are both examples of what I call a register category. And we can define other register categories, although I don't know any useful other ones, but at least we can, at least these two cases are covered. So I just copied this here that you get a vague impression. I don't want to go through the details unless you're interested specifically, but basically what you have in a register category is it's actually kind of two categories because it's a category of objects. The objects are our updates, like the operators in the quantum case, the partial functions in the classical case. And then we have morphisms between them, which for technical reasons are not the registers, but I call them pre-registers. And they have a few simple natural properties and a tensor product. And then additionally, I need a subset of these pre-registers that have to be called registers. They also need to satisfy a few simple properties. And as soon as I have that, I get all the theory, like all the rewrite rules, all the notions of compatibility, the possibility like of rewriting, unfolding, packaging, and all these things. They are all consequences of these few laws. So, one extensions that might work, might be fitting here is, for example, a joint classical quantum, so something that encompasses memories that are somehow not purely quantum, but quantum classical, and I could have any kinds of operations in these. But so far, the only two concrete examples are the quantum and the classical register categories.
All these objects share a memory?
Sorry?
Do all these objects use the same memory? Or
No, and the objects are basically the types. So, but they're not exactly the types, but they correspond to the types. So for every type, like for example, the type of the whole memory, the corresponding object are the partial functions from memory to memory, the classical setting.
Yeah.
Or in the quantum setting, it would be the bounded operators from the memory space to the memory space.
Right, so you have this second order, you have this other composition where A is in memory M and M is in memory set, then you can compose them.
Do you mean that this mapping from A to M?
And then M is, again, can be considered as a register.
Yeah, exactly. This is because these A and M, they are objects, and therefore the morphisms between them, they are like transporting one to the other. And then we have like, well, we have two kinds of morphisms. We have the pre-registers and the registers, because some of the axioms have to be expressed. I mean, it's just for stating these axioms, we need the two kinds of things. In the quantum setting, for example, the pre-registers are simply the linear functions. But that's a technicality. In the end, you only use the registers. Yeah, then, okay, yeah, lots of stuff, nice examples. One last thing that I wanted to mention, for time reasons, without going into the details, I've implemented the register theory in at least in the finite dimensional case, because the infinite dimensional case needs a bit of functional analysis that, like the tensor products and so on, they need a bit of heavier foundations, but the finite dimensional case is fully formalized. And I made a simple example of a very elementary, very simple Hoare logic. And it turns out that, like, defining a Hoare logic, you think it's actually not so easy, especially if I want in the quantum setting and I want to be able to have some expressive way to write pre and post conditions that are essentially subspaces of the space of all possible memory states and so on. It turns out, I think it was something like 50 lines or something to define the language, a very primitive language, the Hoare logic itself, and syntactic sugar for writing the operation. And that used very heavily this register formalisms, because almost everything that happened was just kind of wrappers around invoking registers. And you can now write pre and post conditions like my precondition is that registers X and Y jointly are an EPR state, and register Z is orthogonal to Ket0 or something. You can write these things purely as syntactic sugar around the register formalism. And then I used it to analyze the teleportation protocol. That's a bit more lengthy. I think it's maybe 200 lines or something, because in the end, you still boil it down to showing that certain products of matrices do something. But the nice thing is that it was possible to do it like completely generally by saying, well, we have just these registers and they're compatible. So the whole proof is now doesn't care about how these registers are actually arranged in which order in memory and so on. And you get within just a few lines of code, you can specialize it to concrete cases, which I think would be much more difficult to do if you were in one of the other ways how you could formalize.
So I think I'm kind of now understanding more your goal, right? So
I
would it be like fair to say that what you want is to have a language which almost looks like the kind of pseudocode that you would have in a quantum algorithms paper, but which has a formal meaning, has a formal semantics.
Yes, yes. But the thing is, I don't want. My goal goes beyond just wanting a programming language. I also want it, for example, in formulas. So if I just derive like this and that are the same unitary, then I also want to be able to. So it's kind of in a sense a bit of a made-up pseudocode. So I don't want one concrete language with concrete operations.
The notation that you would use in pseudocode, maybe.
Yeah, or maybe not the notation I can make up, whichever I want, but basically the concept of a variable. And it turns out that this is something that I can separate from the concrete language semantics. While most of the time you have this notion of what would be, for example, x semicolon phi 1. This is kind of hard baked into the semantics, and semantics get more bloated because someone needs to figure out how to apply C0 to these things and so on. So you need to unwrap, wrap, and so on. So you get also a much nicer separation between the concept of a memory location and then the rest of the semantics. But it's definitely one possible goal is this. Another goal is like here we have pre and post condition, which is not what you usually call a programming language. It's more like a language for writing expressions. It also uses the same formalism. So it's something for more than one purpose. Yeah. And I think even the classical thing, although the need is less strong, but I think the classical registers, they also are useful, because I think you can write some like classical imperative languages more easily if you don't need, for example, an assignment. If you want to assign to a pair, you would usually have to write your semantics differently than if you just support assigning to a single variable. With this formalism, assigning to a pair does not need an extra definition, so it could also streamline classical or logic.
Also, I guess you can do some separation logic.
Sorry?
Also, I guess you could do separation logic.
Yeah, I think, I mean, it sounds at the first glance very related, but I think it addresses a bit different concerns, because this is more like kind of statically fixed variables. Like
The issue of compatibility is not super.
Yeah,
That's similar. Right?
that one, yes. So there could be interesting connections, but at least at the present stage, it seems a bit different, because separation logic, it does not give you really a nice way to refer to a data structure as an object on its own. It's basically just you still need to follow the pointers yourself. You just have the guarantees that it will not run into the other pointers, or like depending on what your assumption is. But it's still kind of, at least on my elementary knowledge of separation, it does not help you to abstract away from the fact that the data structure is some pointer following data structure. Yeah. While a register, you could have a register that refers to you could have like present one data structure in the memory in two different ways, and this would both be valid memories, so you can abstract from the internal thing. On the other hand, what is not, at least not in the way it is now, what you cannot do is you cannot refer to, for example, a linked list as just its content, because of the fact that the position is kind of dependent, like where it is in memory also depends then again on what it is, and it doesn't fully fit. But it seems that would be something really cool if you could somehow define registers that could really express, well, this is the content of my linked list. That only works if the linked list is in a fixed place in memory, which it isn't. So not sure to what degree this can be overcome or not. It's at least not trivial. And maybe some combination of separation logic and registers could even give you something there, but that is just speculation. Yeah. So that's kind of the register theory stuff that I wanted to show you. Happy to discuss anything about this.
Thank you very much.
I apologize. I had misunderstood what the point of this was during our discussion before. Now that at the end of figuring out.
But I mean, if we are in a strict category, then things are simpler. But I think I don't know whether we can get strict categories at any reasonable level of effort.
I don't know. I still think that the strictness is some kind of red herring, but I think there are two different things here. Like certainly, if you want to write pseudocode and you want to use sort of variables, then you need something like this, and I think this theory is very important to know. If you want to use a variable less, like without a variable representation, then I think it's sort of these kinds of diagrams, like circuit diagrams that you start with.
Yeah,
and there's a whole group. I don't know if you know about this group in Oxford.
Yeah, I know
these kinds of diagrammatic calculi.
Yeah,
but taking the kind of the variable-free approach, and I think their goals are very similar to yours in some sense.
Maybe, but I think that these diagrammatic things, they hide a bit the true complexity, because if I want to like really say what these diagrams mean, so let's say I don't want to, for example, use a logical tool that has diagrams built in as basically its axiomatic foundation. So not something that on the lowest level reasons about diagrams, but something where diagrams are maybe something that helps the user, but we still have a traditional logic in the sense that anything is represented by terms. So if I want to represent this diagram by terms, well, if they say it's a monoidal category, then actually how I understand it is, I see a diagram, I can translate this diagram into a formula.
Which is what you've been doing at the start of your talk.
And that's exactly what I thought. So if I actually if I say I cannot rely on visual aids, I can only rely on terms, then I feel that you will end up with, I mean, the definition of the symmetric monoidal category explicitly mentions all these things. So the only thing is that the properties of
terms are visual aids too. I just want to put this out there.
yeah, but they are kind of also an abstract concept. I mean, I'm not meaning the written down term. I mean, like for example, if you write a theorem proof, or if you take the traditional mathematical notions of a proof, it's something like a sequence of operation, either on terms or on strings, depending which view you take. It's usually not on pictures.
But there's a difference between these diagrams, these circuit diagrams, and arbitrary pictures, in that they correspond precisely to terms, right?
Well, they correspond to sets of terms, but sets of terms that are equal.
That are equal according to the law. So the thing that
the nice thing is you don't have to pick a representative.
Yeah, exactly. But the not nice thing is that that you are kind of I feel that you're a bit like, if you actually reason on the pictures, you are using like your visual understanding, and you know that you could represent it in the terms, but I mean, the proof that all these things work, they actually are also not on pictures like things with pixels or whatever. They are also on some abstract representation. So I feel we have this larger gap, and I'm not saying it cannot be filled, but I'm saying that if you write a foundational theorem proof that doesn't want to take specifically these kind of pictures for specific symmetric monoidal category as like a built-in data structure, but you want to really break it down to a lower logical foundation, you will have to work with these objects like the swaps and so on.
Yeah,
You can hide it from the user, and that can be very useful. But I think in certain aspects, it's tempting to think that things are simpler than they are, foundationally at least.
I agree with you, and I also agree with Pavel that to some extent your goals are parallel, and that like what you're doing is also quotienting a set of equal terms, for example, the ones with different parenthesizations, right? And just giving one representative, and you say, well, which one do you mean? You say, I don't care. Because they're all equal.
Yeah, in that sense, it's similar.
Well, indeed, if they don't do the same thing, then one of them is wrong, because they're about the same thing.
Yeah.
Right? So we should.
Although I have one goal that is not something that would be covered in the diagrammatic thing, at least not as far as I can see, that where you say I have the same register twice. Like I have, for example, the position and the momentum of a particle. I cannot have two wires in the diagram that are this, because basically whenever I cut through a diagram, all the wires that I've just truncated, they would be compatible registers in my notation. So you cannot talk in the same diagram of X and Y together and of Y separately. So you can either have a wire that is X and Y together, or you can have X and Y, but you cannot refer to both of them kind of in the same picture. So I mean, it's not even meaningful what that would mean in that approach. So it does have, while in a program, you may want to do that. I mean, you will have to be aware that doing something on one affects the other. But that's okay if you're aware of it. You may want that. You may want to say, I first do something on X, Y, and then something on Y. So it goes along a different philosophy in that respect. I mean, also because their purposes are different. I'm not saying that it's wrong that the diagrammatic approach cannot write that. If you would write that in the things that you use the diagrammatic approach for, it would lead to something really weird. So the motivation is a bit different.
The box with two things going in and two things coming
Yeah, but that's an explicit conversion. Like then what comes out is a new register or a new variable.
Oh, I thought in your convention, if I do Hadamard to X, then the output of that is still called X.
Yes.
We could do the same thing. We could name the wires that way and say this register is X. It's always this wire. Its operations are all linear.
Yeah, but it's different. In that case, it's just your choice of, it's a naming choice. I mean, the names are in that. Here it is actually the same register in a semantically meaningful way. Because, so the diagrams, they're in a sense more like a functional language. They are describing functions, like you have a bunch of things come in and a bunch of things come out, but there's no notion which that comes out is which that came in.
But in the quantum world, there is, because all of your operations have the same number as inputs and outputs.
No, they don't.
Are you sure? Oh, the measurements don't.
The measurements might not, also isometries might not. Also, the thing is that, yeah, so that they don't, and even if they do, there's no canonical reason why the left output corresponds to the left input.
Sure.
Yeah, well, here it's not more like this imperative view, like we have the memory, and we have mutable elements, while the pictorial approach, it has like input output, but there is no state. So this is very useful for imperative view of things, and the pictorial diagrams are more functional view.
I don't agree with you. Fine, I don't.
You know what this work that is called quantum circuit architecture, where they define these diagrams. So this is from the University also, where they define these diagrams, and then they put this hole, and then I think they get, or once they put a diagram with a hole, is exactly, I think it's exactly.
Sorry, I didn't fully understand.
So there is this work called quantum circuit architecture.
Yes.
Where they define diagrams, and then they use holes, and that do something, the same motivation that we have for
Holes.
resistors. Like they do diagrams that have in the middle, something where you could put potentially some.
Yeah.
And then when they do that, I think they get the definition of when you instantiate it on Hilbert spaces, I guess precisely the definition that we have of what quantum register. So it's a linear A to A that goes to a linear N to N. So I think there is, this was just to ask.
Yeah, so it could be that this kind of circle with a hole might be a register, give a register in my setting.
So I think it's exactly, so you can show.
No, in general, it will not be multiplicative. Because if you take this thing with holes, like, if you have, I don't know, let's say we have U and then the hole, let's say this is my F. Then I do not have that F of A times F of B equals F of AB, because this one on the left side would be U, B, U, A, and this one here would be U, B, A. So it's, at least it's not it doesn't satisfy the axioms of registers then. Not even the one that is like, definitely the one that is needed for a register to actually fit the intuition. The other things like that, linear and so on, I mean, this is just because we like linear, but it's not kind of something that obviously follows from the idea of registers. But the multiplicativity is really something that is built into our initial goal. I mean, assuming that I understood right what you meant by circle.
Yeah, I'm not sure about that, but okay, but I think it may have some connection there, because I'm quite sure that it should be the same thing. So vision should be the same thing, and now I don't know how to work with multiplicativity.
Yeah.
But, thank you.
Yeah.
Thank you for that.
I mean, you could have specifically a class of these circuits that would be multiplicative. Also, the adjointness would be difficult. So you also don't get that. You would also need, for example, that doesn't hold is that U, A, dagger is not U, A, dagger. So actually, the only functions that are registers in a different representation of registers are the functions that are of the form f of A equals U, A tensor identity U dagger for a unitary. So that's mathematical corollary of the definition. So it's actually quite restrictive.
Thank you very much, Dominic. Plenty of questions during the talk. I think maybe
Thank you.
you will be around today for.
Yes, I think so.
Yes, some extra discussion. Let's thank Dominic.